Hello everyone. So in this video, we will talk about hypothesis testing for proportions. Okay, especially here we will talk about hypothesis testing for single proportion. By proportion, we mean, for example, the proportion of the students in a university who favor Starbucks over Cafe Nero, for example, or the proportion of students who are fan of Beşiktaş, for example. So we will talk about these proportions. Well, first we will talk about the relevant test statistic. Then we will deal with so in this slide we will deal with the hypothesis testing. Okay. Then we will talk about confidence intervals, and later we will talk about confidence intervals and hypothesis testing of two populations. Okay, so this is the third. This will be the third slide set. Well, so remember when we were trying to talk about the sample, the population mean mu, we just use its point estimator x bar, and we talk about its distribution. Okay, its distribution, and then we talk about its parameters, which are in fact the expected value, the mean, and the variance of x bar, right? The variance of x bar, right? Now we have a population proportion P. For example, the proportion of people, students in university who favor Cafe Nero. Okay. So it's very hard to calculate again the population proportion. So what we did is we take a sample and just like we calculate X bar, we calculate P hat, the amount of people who like Cafe Nero. Okay? So just like X bar is a point estimator for mu, P hat is a point estimator for P as well. Okay? So the sample proportion P hat is equal to X divided by N. So what is X? X is, in fact, let me see if I have it there. So X, in fact, is the total number of, let's say, number of people, okay, number of people who like Cafe Nero, okay, who like Cafe Nero, divided by total number of students in a class. So how can we calculate p hat in our class, for example? We can ask the students, you like Cafe Nero? Do you like Cafe Nero? Ask everyone. And just count the number of people who like Cafe Nero. Let's say, for example, there are 13 many students. And if the n is equal to, I don't know, let's say 39, then p hat is equal to 1 over 3, right? So the proportion of people who like Cafe Nero will be, the sample proportion will be 1 over 3. So in fact, so what is x? What is x here? X is simply the number of people, total number of people who likes Cafe Nero. So for example, if you just if you say n equal to 30, if we have 30 students in the class, okay, then x1, x2, that I have what x30 here, and each of them is a binary variable. Binary mean well, it has a value of 0 or 1. Okay, it has a value of 0 or 1. So if he likes or she likes Cafe Nero, then the value of x1 is 1. Otherwise, if he doesn't like it, then the value is equal to 0. And this is also 0 and 1. And I have 30 many students, it's 0 and 1 as well. Okay. So I just sum them up. Okay, I just sum all of them, right? I from 1 to 30. Okay. So some of them are 1, some of them are zeros. If you just sum them up, and let's say if the result is equal to 15, for example, it means that there are 15 many people who likes Cafe Nero. Then what we do is we just divide it by the total number of students, which is 30 here, okay, and divided by 30. That's equal to 0.5, which is my p hat, right? This is my p hat. So, well, what is x? Well, x has a binomial distribution, okay? So what is x? X is a binomial distribution. So remember binomial distribution. In order to know binomial distribution, first we need to know the Bernoulli trials. So a Bernoulli trial, let's say xi, let's say, is equal to either 0 or 1, right? So the outcome can be 0 or 1. So it's a random variable who has only two outcomes, 0 and 1. And the probability that you have 1 is p, the probability that you have 0 is 1 minus p. So generally, we just denote this one as a success and 0 as a failure. So it depends on you which which part of your trial to be labeled as success and which part of your experiment should be labeled as a failure. So for example, in our example, 1 is a success. It's the number of, these are the people who likes caffeine. Okay. So this is a Bernoulli random variable, okay, Bernoulli. So sum of, if you just sum n many Bernoulli trials, then the resulting random variable is a binomial random variable. Remember, binomial random variable has two parameters. First, n, how many Bernoullis you are just summing up, and p, what is the probability that each Bernoulli has a success, okay? So binomial random variable again counts the number of successes in n experiments and where p is the success probability. So the expected value of a Bernoulli random variable, okay, so this is mu, sorry, not binomial, but binomial random variable. The expected value of binomial random variable is n times p, and the variance is n times p times 1 minus p. Sometimes we denote 1 minus p as q, okay? So this is in fact n times p times q, right? So x, which is sum of xi's, okay, n many xi's, I from 1 to n. So the expected value of x is equal to n times p, and the variance is equal to n times p times q. Okay, so that's great. Why? So why do I need this? Why do I need this? I need this because, so remember, we say that, well, I just want to find mu. I want to say something about mu, and the way to say something about mu is I will look at the x bar. So first we look at the parameters of x bar. It's mean, mu of x bar, let's say, and its standard deviation sigma of x bar and its distribution, okay, its distribution. So now I have p, the population proportion. So in order to say something about p, I will look at p hat. So what I need is I need mu of p hat, right, sigma of p hat, and then I need distribution of p hat, right? Now, the thing that we did here is the first step to find the parameters of p hat. Why? Because p hat, okay, p hat is simply equal to x divided by n, okay? So we know that x is a binomial random variable and expected value of x is equal to n times p, okay? And variance of x, which is also sigma square of x, right? This is equal to n times p times q, okay? So that's great because I know the expected value and the variance of x, so I divide it by n, by a scalar. So it's very easy to calculate the expected value and the variance of p hat. Expected value of p hat is equal to that's simply equal to n times p, right? Divided by n, which is equal to p. So that's great. The expected value of p hat is equal to p, which means p hat is a unbiased estimator of p. Okay? And the second thing is the variance of p hat. The variance of p hat is equal to, so that's x divided by n. That's equal to variance of, in fact, x divided by n squared. And this is equal to n times p times q divided by n squared. And this is equal to p times q divided by n. So this is the variance of p hat, and this is the expected value of p hat. Okay. So this is what we have, right? This is the expected value of p hat that's equal to p, and this is the variance of p hat, so the sigma square p hat, that's equal to p times 1 minus p divided by n. And one good thing is that, well, let's go back. One good thing is that, well, p hat, which is equal to, in fact, sum of xi over n. So just look at this. What you do is you just sum the values of xi and divide it by n. So in fact, this is a kind of a sample mean, okay? This is a kind of a sample mean. And sample mean, what do we know about sample mean? Using central limit theorem, its distribution is approximately what? Normal, right? That's great. So now we know everything about p hat. So p hat by using it's a sample mean, hence we can use the central limit theorem, which says that well its distribution is normal. So how about its expected value? Its expected value is p. How about its sigma squared p hat? Its variance. It's equal to p times q divided by n. Okay. So now we are ready to infer information about unknown parameter p. So p hat, again, p hat is normally distributed. Sorry, is normally distributed. Okay, let me just take my eraser here. Sorry. So p hat is normally distributed with its mean p and its variance or standard deviation pqn, okay, and its standard deviation we just take the square root of it, which is pq over n. So since this is normal, then if we just subtract its expected value and divide it by its standard deviation, then this is a what? This is a standard normal, right? This is a standard normal. That's great. That's a standard normal random variable. So let's talk about hypothesis testing. So this is, well, this is my test statistic, okay? P hat minus P0 divided by P0 times 1 minus P0 over n. So of course, let me just first write what is step 1. Step 1 says that H0 is equal to P0, some P0, some value. H1, P is not equal to P0. Of course, you can just make two-sided tests or one-sided tests, but for now, let's stick to the two-sided test in order to understand whole procedure well. Okay. Um, so P is equal to P0 versus P is greater than P0. Okay, so this is a greater than hypothesis, greater than type hypothesis. So if your Z observed, okay, if your Z observed is greater than Z alpha, right? So this is a greater type of alternate hypothesis, then you will just reject H0. So if P is smaller than P0, okay, so this is a smaller than type of alternate hypothesis, then you will reject the H0 if Z is smaller than minus Z alpha. Okay. And if P is not equal to P0, if this is a two-sided test, then what you will do is just check whether Z observed, right, is smaller than or equal to minus Z alpha or Z is greater than, Z observed is greater than Z sub alpha over 2. Well, so this is applicable. So this is an approximation, right? Because we said that okay, p hat that's equal to xi over n, and so this is a sample mean. So sample mean can be approximated using central limit theorem and so on and so forth. Especially for large number of samples, this is very useful. But for small sample, okay, for n is equal to, for example, 5, 6, 10, 15, for small sample sizes, generally we don't use the standardized test statistic. We don't use the normal distribution. So what we use is simply, well, X is a binomial, just use binomial random variable. How? We just use the p-value for this kind of hypothesis tests, okay? Okay, so let's make an example. Um, sorry. Okay, so a commonly prescribed, that is a commonly used drug for relieving, just for make people uh, relief from nervous tension is believed to be only 60% effective. Okay, so if people, for those who have a nervous tension, use a common drug and its effective rate is 60%. So experimental results with a new drug administered to a random sample of 100 people who were suffering from nervous tension, okay, show that, well, 70 of them received relief. So what does this mean? This means that, well, p hat is equal to 0.7. Okay? Is this evidence sufficient enough, okay, to conclude that the new drug, okay, this new drug is better than the current standard relief 60%? That is it better than the one commonly prescribed? Please use alpha equal to 0.05 significance level. That is, I want to test whether, let's say this is P, P, so this P, first let's define P, okay, so let me just erase, okay, so P is the relief rate, for the new drug, okay, for the new drug. So I just want to test whether this thing is, let's say, smaller than 0.6 versus the new drug, is it greater than 0.6? Okay, so remember this is equivalent to testing p is equal to 0.6 versus p is greater than 0.6. And so my evidence p hat, that's equal to 0.7. My evidence just supports the alternative hypothesis as we expected. But I want to test whether this is sufficient enough. Okay. So what we will try to do is first just look at the z critical, okay, which is, so this is z sub 0.05. So this is equal to 1.645, right? And p hat is equal to 0.70, okay? And my z observed, so this is my test statistic, remember, this is my test statistic. From here, I will calculate the z observed. How? Just plug in the values p hat 0.7, p0 0.6. This one just comes from the null hypothesis. Okay, this is from h0, and this is just coming from h0 as well. Okay, divided by 100, that's equal to 2.04. Okay, well, since 2.04 is greater than 1.645, we will reject h0. Okay, so what you can do is you can also calculate probability that z is greater than 2.04. Okay, so what is this probability? Remember, this is you observed. The probability that your test statistic is, let's say, worse than observed z, right? So this is, okay, this is 2.04. I'm just calculating this area here. And this is what? This is, remember, this is the p-value, okay? You can just calculate the p-value. So the p-value, let's try to see the p-value. P-value is z is greater than 2.04, which is almost, let's say, it's smaller than what, let's say, almost equal to 2.0207, and that's very small, okay? Hence, we can say that, well, the new drug is superior to the commonly used drug, okay? So again, how can you find this? You can find this 1 minus norm, okay, this is from Excel. You just write the value, which is 2.04, the mean, okay, so this is mu, right? This is your x value, okay, x value mu. Then you just write 1, which is your sigma, and write 1, okay, and this is your f, or let's say CDF, okay, CDF. This is your CDF. If you just write 0, okay, well, again, if this is 0, this is 0, then you get what? Then you get f of x, okay? So here it just gives the capital F of x, right? Well, This was, so up to now, we were talking about hypothesis testing when sample size is a bit large because we use central limit theorem. As you might recall, central limit theorem works fine, okay, works fine when n is large, when n is large, especially when n is greater than 30, okay? So what happens if we have a small sample? Then testing the proportion in a small sample is the procedure is similar to the previous cases, but now since since we will use, as we will see, binomial distribution, this is a discrete case. Hence, we will just evaluate the p-values. Okay, so first just write the hypothesis, which is p is equal to p0 versus p is greater than p0 or smaller than or not equal to. Okay. Well, choose your alpha and then choose your test statistic. Now, test statistic is x, and x is a binomial random variable. Okay. And the next step, just compute the p-value. Okay. Just compute the p-value based on your observed value of x. Then make your decision. Okay, so for continuous, for discrete random variable, well, it's a bit hard to just visualize it, but in the example, we will see it will be crystal clear in your head. So a builder claims that heat pumps are installed in at least 70% of all homes constructed after 2000 in Istanbul. Okay. A real estate agent disagrees. He says that no, it's not, and claims that the actual percentage of such homes with heat pumps is much more less. So what they do is they just pick a random sample of 60 newly built houses, and it turns out that 35 of them has an installed heat pump. Okay, so 35 of them has an installed heat pump. So what is p hat? P hat is equal to 35 divided by 60. Okay, which is equal to 7 over what? 7 over 12. We will see. It's, I don't know, but something like 58, something like this, right? Well, just devise a hypothesis testing problem to settle this argument down. Just use a 0.10 level of significance, okay? So first, this is my hypothesis, right? P is equal to 0.07. This is my null hypothesis, or P is greater than. And this is the real estate agent's claim. He says that, well, P is smaller than 0.7, okay? So remember, my P hat is equal to 0. If I'm not wrong, 583, okay? That's great. So as you can see, this thing just supports the alternative hypothesis. Okay, don't forget this. If your data does not support the alternative hypothesis, then there is no meaning of making a hypothesis, that you cannot reject the hypothesis. So if the data suggests supports the zero the let's say if it supports the null hypothesis, then can't do anything. Okay, so there is no need to make any hypothesis test because, well, your evidence already supports the null hypothesis. So hypothesis testing is meaningful whenever your data, your evidence supports the alternative hypothesis. Okay, so the test statistic is x, which is a binomial random variable with what? With H0 is true, okay, with p is equal to 0.7, the probability, and with n. Okay. So the sample proportion is okay, 0.583, which is an evidence for H1. Okay, so my X observed is 35. Okay, so what does this mean? This is N, right? This is N. Um, N is equal, so this is not N, but this is X, sorry. N is equal to 60. Among 60 many houses, okay, the probability is I just see that there are 35 many houses that have a heat pump, okay? So what is the p-value? P-value is probability that there are less than 35 houses when p is equal to 0.7, okay? So assuming that H0 is true, so this comes from the H0. I just find the probability that there are less than 35, probability of having less than 35 many houses. Why less than? Because, well, I'm just testing as an alternative P is less than 0.7, okay? So if X is less than 35, for example, if X is equal to, I don't know, If x is equal to 15, right? Then your p hat is equal to 15 divided by 60, which is equal to 1 over 4, which is far more smaller than 0.7. Okay, so how you just select whether this is greater than or equal to, you just look at the null hypothesis. Okay, so if the values here favor the alternative hypothesis here, then that's okay, right? So what you do is you just sum the probability from 0 to 35, okay? And you can just find this either in Excel or either in your book. It turns out that this probability is equal to 0.0362, which is 3.62%, almost equal to 0.04%, okay, or 4%, let's say. So this is your p-value, right? What was the alpha value given? Alpha value was 0.10, and since 0.04 is smaller than the alpha value, then you can just reject. You can reject the null hypothesis. You can reject H0. Right? So the data support that the real agent's claim, who says the true proportion of homes with installed heat pumps is far below or below 70%. Okay.